Hi everybody. So today we are talking about generalized vertigo maps. So we are talking about basically maps with hidden attractors, as I will show you later. This is from a recent publication in International Journal of Bifurcation and Chaos, very well-known journal, of course. The paper is called Generalized Vertigo Maps, a new family of chaotic maps with robust chaos and without fixed points. Okay, in the description of the video, I'm going to put a link both for the paper and also for code in MATLAB to generate the prbg that I'm going to show you. Now, we are talking, as you remember, basically about chaotification. The idea is that we take existing maps, logistic, tent, sign, renouille, whatever, and we're creating new family of maps with new properties, desired properties. Coexisting attractors, no coexisting attractors, robust chaos, hidden attractors, whatever. Okay. So in this work, we are basically extending a work from a previous publication by Jafari et al. From 2016. And in the original paper, what the authors did, let me move my camera, they basically took the logistic map and they reshaped it and remapped it in a piecewise function. So they had two subfunctions in such a way so that one curve of the logistic map was above the bisector and another curve of the logistic map was below the bisector. Okay, and this family, basically, as you know, in discrete time, when we don't intersect the bisector, we don't have any equilibria. And they saw that this family had hidden attractors. In our work, we generalized this idea by doing what? We added four parameters, P, Q, A, and B, and with these parameters, we sort of rescale and resize the curve of the function. Okay, so we move it horizontally and vertically, we rescale it, that's what I mean, in such a way so that we can change not the shape of the curve exactly, but the rescaling of the curve. And with this way, we generalize the original work. Okay, basically what we do with these parameters is have this box right here that controls where exactly the shape of the curve of the function will lie. Okay, so we generalize the original work by rescaling the curve of the function. And we have a lot of theoretical results regarding this new family of maps. I have a couple of here, but there are more in the paper. Some of them have to do, the most important, I believe, has to do with the Lyapunov exponent, because we actually saw that the Lyapunov exponent of the new family is identical to the Lyapunov exponent of the original map that we are using. Okay, you see here the logistic map as an example. And we also have some results regarding the absence of equilibria, because we don't have intersections with the bisector, and the absence of some specific periodic behaviors. For example, odd behaviors do not exist here. So we consider different families of seed functions. For example, the first case we had is the well-known logistic family. Okay, you see here some examples of generalized vertical maps. You see in each case that we have one subfunction above the bisector, one subfunction below the bisector. So we don't have any fixed points in all of these situations. And you see that the shape of the function, okay, is either pushed vertically or pushed horizontally. So we have a different shape in each case, which is basically based on the logistic map. Okay. Uh, the bifurcation diagram here is kind of reminiscent of the original logistic map because we see a period doubling root to chaos, we see some crisis phenomena, we see some fractal patterns, but diagram is not identical, of course, to the logistic map because we see it has two sub-regions, which of course have to do with the fact that one function is above the bisector and the other is below the bisector. Okay, so we never we kind of jump back and forth between the two different smaller attractors. Okay, we also have here a color-coded version of the bifurcation diagram from our previous paper. This is very interesting because, as I told you, we have actually shown that the new family can achieve the same Lyapunov exponent compared to the original map. So if we fix the parameter of the logistic family to 4 and change the other parameters, we will constantly have a positive Lyapunov exponent. And we actually show it here. This is a graph that represents different parameter values A and B, and the color represents the Lyapunov exponent. And actually what you see is that we always have a value around 0.5, which means that across all of these different parameter values, the map is constantly in chaos. So we have robust chaos achieved. Very, very nice result. We were going after this result actually, and we achieved it. We considered another family as an example, the very well-known tent map. Okay, you see some examples right here. You can observe again the rescaling up and down of the functions curve for the original tent map. Again, we achieve absence of equilibria. We have no intersections with the bisector. And the original tent map, actually, if you remember, has robust chaos. So this is a good result because here we also have robust chaos. So the bifurcation diagram, as you see right here, has again two scales, two smaller attractors. It is chaotic everywhere. And indeed, this generalized vertigo family from the tent map achieves robust chaos for all parameter values. So this is a very, very nice result. Now, to test these maps, we consider the pseudo-random bit generator. I have this in other papers as well. Here I have a bit generator that is a bit slower than other ones, because in previous videos that I have, the generators were much, much, much faster. This generator is a bit slower. Actually, the speed is around 1 megabyte per second. It is a good speed, but other papers can achieve faster speed. 5, 6, 7, 10, 15 megabytes per second. Okay, so it's not the fastest of the prbgs, but we experimented with the use of the exponential function. Okay, so we have e to the x and pi to the x. Both of these functions, these exponential powers, are a bit slower, and that's why the generator is a bit slower, but they introduce a lot of nonlinearity, and this increases, of course, the randomness of the generator. So we tested both of our maps with two different keys. So we tested 4 different cases. All of them pass the statistical tests. So this prbg can be used. I'll put the MATLAB link in the description. Can be used in any application that you like, and especially if you are not really interested in having a fastest speed, you can use it as you like. Okay. I believe if you test this generator with other maps, you will also going to achieve randomness because the e to the x and pi to the x are actually very, very good functions because they have a very high nonlinearity. Okay, so we have a very nice working prbg that passes all statistical tests. It's just a bit slower than others. Okay. Now, this work has a lot of extensions that we are keeping in mind at the moment. Basically, for me, the most important extension that should be done is the second one. Okay, we consider piecewise functions with two pieces, with two sub-functions. Okay, one above the bisector, one below. We can consider more sub-functions. The original paper by Jafari et al. Actually did that. I believe we can actually do it here as well. Create maps that have 3, 4, 5, 6, 7, 8, 10, many, many, many sub-functions, and of course at the same time achieve robust chaos and absence of equilibria. So this is a very interesting application. We are working on its extension. Possibly we will work on that on some journal or maybe some conference article. Okay, this is very important. Of course, what we are interested in is also proving that, proving theoretically that we don't have coexisting attractors. We searched, we didn't find coexisting attractors. Actually, there are not coexisting attractors, but we need to prove that as well. And also, of course, a fractional version of this family can be done by anyone who is interested, but also we are interested in developing networks of maps. Networks are actually a couple of maps that are in a series connection, and the value of the first map is fed into the second, the value of the second map is fed into the third map, the value of the third map is fed into the fourth map, and so on. And this is very interesting because these are maps that are, in coexistence or in connection may have similar or different behaviors. So they may be all periodic, all chaotic, but you may have some periodic and some chaotic maps coexisting. Okay. I don't know how the system will behave if we connect a couple of these maps together. It's a very interesting topic of study. Okay, so many, many, many more applications can be developed from this specific paper. Okay, I'll put a link to the description and also a link for the prbg in MATLAB. And thank you very much. If you have any questions, write them down, and I'll see you in a later video.